Now, chemical kinetics is the study of rates of chemical reactions, and this tries to answer the question, when will a reaction occur? And the collision theory is kind of answers this question. So one thing about collision theory shows that chemical reaction will occur when particles hit each other. Particles have to hit each other in order for a reaction to occur. That's like the most simplest thing. Second of all, particles have to be in the correct orientation. So let's say we're given this reaction below where A reacts with BC to form AC and B. Now, what if A hits BC in a way where A is hitting the B part of the molecule? This reaction is not going to occur. But if A is hitting the C part of the molecule, then with enough energy, right? This brings us back to the third thing about collision theory. There has to be enough energy for a reaction to occur. With enough energy, yes, this reaction will occur. Say we have a reaction where we're putting like atom A inside a container filled with water. And we're putting the same amount of water and same amount of atoms, A atoms, inside the, let's say, beaker. Now, what you'll find if you see there's a temperature difference, and what you'll find is that the beaker with a higher temperature reacts more, okay? So the rate of reaction for the beaker with a higher temperature increases. As temperature increases, rate of reaction increases. Now, why is that? Well, temperature is the measure of the average kinetic energy of particles. So as temperature increases, right, the average kinetic energy increases, okay? So basically the particles are moving faster. And when we were talking about collision theory, we know that particles have to collide for a reaction to occur. And if the particles are moving faster, there's going to be more collisions, which means the rate of reaction is going to go up. In addition, think about it. If we have particles, they're moving super, super fast, they're going to hit with more power. There's going to be more, energy associated with these collisions. And as we know, particles have to hit each other with enough energy for a reaction to occur, which goes back to collision theory. So if energy increases in the collisions, reaction rate also increases. Now let's say we kept the temperature and the amount of water we were using for the reaction constant. And instead, what we did was we increased the concentration of A. And what you'll find out is if you increase the concentration, the rate of reaction will increase. So there's going to be more products formed. Why is that? Well, let's take a look at a molecular level. What's happening at the molecular level? As we increase the concentration of A, you can see that when there's more of it, the amount of collisions will increase, right? So think about the amount of collisions in this area. So I'm referring back to the first kind of beaker compared to the one with the second beaker. If the particles are moving at the same speed, but there's more of the particles, it's going to hit the water molecules more. And we know that as the amount of collisions increases, the rate of reaction increases, which is why as we increase the concentration, the rate of reaction will increase. So imagine atom A in its solid state, okay? So the amount of water and the amount of atoms we have stay constant. And what we did in the first container is imagine atom A as a solid. And all we did, we put this solid into this water, same amount of water. And in the second container, you'll see that we broke this big piece up into tiny little pieces. Still the same amount, and we put this inside the container. And what you'll find out is as the surface area of your reactant increases, the rate of reaction will increase. So you'll find that you're going to form more products in the second container than in the first container. Now, why, when we increase the surface area, will the rate of reaction increase? Well, in the first container, when you put like the solid atom A into the container, the reaction is only limited to this area, meaning that we know that particles have to collide in order for a reaction to occur. So if your reactant is here, well, this reaction is only limited to this area. But if we break this up into smaller pieces, which increase the surface area, the reaction can happen here, it can happen here. So the amount of particles that hit each other will increase as the surface area increases. Reaction can happen all over the place, which is why as we increase the surface area, the rate of reaction will increase. The final factor that affects the rate of reaction is the addition of a catalyst. And remember how I said that particles have to collide with enough energy for the reaction to occur? Well, what the catalyst does, it lowers the amount of energy. And the amount of energy for the reaction to occur is also called the activation energy. So this lowers the activation energy. And why does it do that? How does it do that? Well, we're going back to our example where A reacts with BC to yield AC and B. And what the catalyst does is it basically orients it in the correct way. So when, the particles are oriented in the correct way, the rate of reaction will increase. So it lowers the activation energy, which increases the rate of reaction. Now, we can actually measure, during a reaction, so reaction progress is on the x-axis. What happens to the potential energy? And we can actually measure this change using a potential energy diagram. Now, this is a potential energy diagram for an exothermic reaction, which means that, let's say if you have, a pot of boiling water sitting in your room, that's going to release energy. It's just a reaction that releases energy, okay? What you'll notice is that potential energy when you started is greater than potential energy when you end. And that makes sense because you're releasing energy. So the energy when you ended is going to be lower than when you started. Now, you might notice this peak right here. I drew an arrow right here. This peak right here. This thing right here represents the activation energy for this reaction. So when you're trying to go from A to B, A and B to C, this represents the activation energy, right? And this is just the minimum amount of energy for the reaction to occur. And when, you see this reaction happening, let's say, under, on a molecular level, what's happening is that as, your reactants are slamming into each other, they're colliding. What happens is this bond right here, if this was a molecule, this is absorbing energy from the collision. So when the bonds are being broken, energy is absorbed. And when this reaches the activation energy, right, let's say this is on the top of the hill, one of two things can happen. The reaction doesn't always have to work. So let's say this bond is actually broken. In the transition state, this bond can actually be reformed and nothing will happen. Or this bond is broken and what happens is a new bond is formed. And when a new bond is formed, this releases energy. I've drawn 6 lines and I want you to predict, what these lines represent. Try to guess. First line goes from the x-axis all the way up to kind of our initial potential energy. And that's exactly what it is. This is just the potential energy of reactants. That's all that is. the second one, you might see that this line represents kind of this line to this line. This represents kind of how much energy is needed to reach the top of this hill right here. And this actually represents the activation energy. This represents activation energy represented as E subscript A of our forward reaction. What this basically means is if we're trying to go from A to B, A and B to C, we have to meet this threshold of energy for this reaction to occur. So we have to reach the activation energy because as our collision theory states, our particles have to hit each other with enough energy for the reaction to occur. And this is the energy needed for the reaction. Our third line, this goes from our x-axis all the way up to our potential energy of our products. And that's exactly what it is, potential energy of product. Our fourth line, this goes from our kind of potential energy of our product all the way up to the top of the hill. And this is actually the activation energy of the reverse reaction. So this basically means that if we're trying to go from C all the way to B and A, right, we're going from here all the way to here, we have to actually meet this threshold of energy in order for the reaction to occur, okay? So if this reaction were to happen backwards, this would be line number 4 would be the amount of energy needed for the reaction. Now, line number 5 just represents the activated complex or the transition state. So this is kind of like the highest point on the hill of the graph. Number 6 represents the heat of reaction or the change in H. This is the same as delta H, heat of reaction. And what this basically states is how much has your potential energy changed from point A when we started to point B when we ended, okay? So how much did your kind of graph change in energy? And line 6 would represent this heat of reaction, change in your heat of reaction. And in an exothermic reaction, this line would represent the energy that's released, okay? So in a chemical reaction, this would represent this line, this part, okay? So the energy that's released would be represented by line 6. So say if the amount of energy released is 55.4 kilojoules, then your change in your heat of reaction will be negative 55.4 kilojoules because you're releasing that energy. Now let's talk about the potential energy diagram for an endothermic reaction. So an endothermic reaction is just a reaction that absorbs energy, which explains why the potential energy of the reactant is in this time, so the potential energy when we started is now less than the potential energy when we ended, because when we ended, we absorbed more energy, so our potential energy is going to increase. And once again, there's this little hill area, so kind of going from this point to this point to the peak, this kind of represents activation energy, and then this is when the bonds, they're absorbing energy. So when bonds are being broken, they're absorbing energy. And then this downward hill represents when new bonds are being formed. And this releases energy, which explains the downward slope. I've drawn 6 arrows once again. And I want you to maybe kind of going back to our exothermic example, going back there, try to figure out what these lines represent. So I just kind of mixed up the order of the lines. Your first line, that's just going to represent the potential energy of reactants, right? This is the potential energy when you started the reaction. So reactants. So it goes from x-axis to potential energy of your reactants. Second line, this is just going to be the potential energy of products, right? This goes from the x-axis all the way to the potential energy of the products. Third line, this is going to be the activation energy for the forward reaction. Just means that if we're trying to go from A and B all the way to C, you have to meet this threshold of energy in order for the reaction to occur. And 3 would represent this. Line forward, what do you think this line represents? This line is actually going to represent the activation energy for the reverse reaction. So if we're trying to go from C all the way back to A and B, we have to meet this threshold of energy in order for the reaction to occur. This is like if the reaction was happening in reverse, you have to meet this threshold of energy. Number 5. Well, this shows, from the potential energy when we started, so kind of this part, all the way up to the potential energy when we ended. So this is going to be your change in potential energy. Change in your H value, change in heat of reaction. So this is basically how much has your potential energy changed from in the beginning to at the end. And in this case, the arrow is pointing upwards because your change in your heat of reaction is positive. Remember back to our exothermic example in line number 6, the arrow was pointing downwards because the potential energy change was negative as it was exothermic. In this case, this is endothermic, so your potential energy change is going to be positive. Finally, number 6, this goes from the x-axis. Might not have drawn it the best way, but this goes from the x-axis all the way to the top of the peak right here. This is going to represent your transition state or activated complex. So when your reactants are kind of transitioning into the products. So once again, if the energy right here, let's say this was 60 kilojoules, well, your change in your reaction, your change in the heat of reaction is going to be 60 kilojoules, okay? So that's just endothermic reactions, so potential energy graphs of exothermic and endothermic reactions. So this is just a simple practice problem. So given this reaction, given this diagram right here, what kind of reaction is this, first of all? And also, what is going to be the activation energy for the forward reaction? So how much energy is it going to take for this part to, go all the way up here and reach this part to react? So the activation energy of forward reaction. Well, we know that because we started off lower than when we ended, we know that this reaction absorbed energy, right? So this is going to be an endothermic reaction. We also know that your change in the heat of reaction, so from this point to this point, right? Let me draw like kind of a line right now. So here. So from this point to this point, your change in your heat of reaction is going to be 55 kilojoules. And we also know that the activation energy for the reverse reaction, so if we're trying to get from this line all the way up to this line, this is going to need 75 kilojoules of energy. So now, if we know this value right here, this line to this line, and we know this value here, this line to this line, well, we can find out the total value by adding these two values together. So to get our answer, we just add 75 and 55, and we're gonna get 130 kilojoules as our answer. So the activation energy of the forward reaction is going to be 130 kilojoules.